Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss second law of thermodynamics and two statements regarding second law of thermodynamics, Kelvin-Plank statement and Clausius statement and its equivalence. Let's begin. First, what is second law of thermodynamics? To avoid the drawbacks of first law of thermodynamics, we introduce second law of thermodynamics. According to that law, second law of thermodynamics specify the conditions for a transformation of heat into work. What is the condition on which basis that heat transforms into work? That is the second law of thermodynamics. In first law, it's not a clear cut idea regarding the condition on which heat converted into work, but second law of thermodynamics clarify what is the condition on which heat transforms into work. So there are two types of statements of second law of thermodynamics. One is Kelvin-Plank statement and another one is Clausius statements. So we have to discuss one by one what should be the statements. First of all, Kelvin-Plank statement of first law of thermodynamics. It states that, what is that of statement? It states that the statement, it is impossible to get a continuous supply of work from a body by cooling it to a temperature which is lower than that of its surroundings. So let me understand it. It is impossible to get a continuous supply of work from a body by cooling and cooling to a temperature lower than that of its surroundings. If we prefer that is a body, this is the body and these are the surroundings. Let it is impossible to get a continuous supply of work from a body. If I try to supply a continuous work from that of body, by what purpose? As cooling it to a temperature which is lower than that of surroundings. Let the surrounding temperature be T2 and the body temperature, this is T2, let the body temperature be T1, where the conditions say that it is T1. If I cool that body, that means the temperature of T1 less than that of temperature of T2, that is not possible. So again I repeat, it is impossible to get a continuous supply of work from a body by cooling it to a temperature. What is that temperature? The temperature is lower than that of surroundings. lower than that of surroundings is not possible. That statement proposed by two scientists, Kelvin and Planck. Statement towards second law of thermodynamics. Next statement regarding second law of thermodynamics, that is Clausius statement of second law of thermodynamics. Same thing, but in a different manner. Let I write the statement first. It states that statement it is impossible for a self-acting body or self-acting machine, we can say self-acting machine when that machine is unaided by any external agency to transfer heat from a body at lower temperature to another body at a higher temperature. Look that statement. We know that the heat transforms from higher temperature to lower temperature body. So here say that if we construct a self-acting body and there will be no such an external agency to transfer that heat from body at lower temperature to another body at higher temperature, that is not possible. The transfer of heat from lower temperature to higher temperature in case of a self-acting body is impossible. That is a statement of Clausius regarding second law of thermodynamics. From these two statements of second law of thermodynamics are the aspects towards what is the conditions on that basis transformation of heat into work is done. So these are the two statements regarding second law of thermodynamics. Now we have to equivalence these two statements on the basis of second law of thermodynamics. Let equivalence these two. Equivalence of two statements. We have to equivalent these two statements. How to equivalent these two? We know every thermodynamic process in nature takes place in such a way so as to increase the entropy of the system. Means from the principle of entropy, we know the principle of entropy as entropy always, the change in entropy of that of system is always greater than 0. What is entropy? Entropy is the degree of disorderness. The degree of disorder of that of system is known as its entropy, and that entropy is always increasing in case of all types of thermodynamic process in nature. But by using that principle, we have to equivalent these two statements that are proposed regarding the second law of thermodynamics. So, in first case that is the Kelvin-Planck statement. So, if we consider SA and SB are the entropies of initial and final states of A and B of that of system. Let I consider a system here. This is the system. It has 2 point A and another point B. A be the initial point, B be the final point, and entropy at initial, that is S of A, and entropy at final, that means at that point B, that will be S of B. So, if I calculate the change of entropy, if I calculate the change of entropy of that of system, change of entropy, change of entropy of that system, it will be, that is SB minus SA, entropy of final to that of entropy of initial, that is integration over from that of point A to B dq by T. dq is the change in heat and T is the temperature. So, that is change in entropy del S, integration from A to B dq by T. And if states A and B are infinitesimal close to each other, these two states are very close to each other, means A point is nothing but that of B point, means that is infinitesimal close to each other. So, what happened here? That is why we can say if A and B points are infinitesimal close to each other, what happens? That change in entropy will be ds is equal to dq by T, which implies dq is equal to Tds, dq is equal to Tds. This is nothing, this is the second law of thermodynamics, that is the second law of thermodynamics, second law of thermodynamics in mathematical form, dq is equal to Tds, dq change in heat, T be the temperature, ds is the change in entropy. And we know that is the principle of entropy, that is entropy of any system, any thermodynamic system in the universe is increasing in nature, that means change in entropy del S is greater than equal to 0. So, according to Kelvin-Planck statement, if we construct a perfect heat engine, if we construct a perfect heat engine, what happened? In case of a perfect heat engine, it is not possible to carry a perfect heat engine. That means in case of perfect heat engine, that converts all the amount of heat, let q amount of heat is taken into consideration from that of source at temperature T, and all that of heat is converted into work done, but it is not possible. Why? If I consider a perfect heat engine, if we consider a perfect heat engine, what happened, such a perfect heat engine exists, then the decrease of entropy of that of source, if that perfect heat engine exists, let we assume theoretically that perfect heat engine is exist, so the decrease of entropy of the source, decrease of entropy of the source will be how much, that is dq by t. dq by t is the decrease of entropy of that of source. Since the working substance returns to the initial state after a completing a cycle, hence entropy of that of working substance will remain unchanged. Look here, the decrease of entropy of that of source will be dq by t, but in case of a perfect heat engine, or we can say it as the Carnot's theoretical heat engine, in that of case the working substance returns to its initial state after completing a cycle. For each cycle we can say the entropy of that of working substance will remain unchanged. Thus the entropy of that of system and surroundings would decrease, which is against the principle of entropy. The principle of increase of entropy, that findings is opposite towards that. Okay, in that it's very convenient to that of what case, Kelvin-Planck statement. According to the Kelvin-Planck statement, we construct a perfect heat engine, then the decrease of entropy of that of source will be dq by t, but which is against that of principle of entropy. Again similarly to equivalent that of Clausius statement, according to Clausius statement of second law of thermodynamics, there cannot exist a perfect refrigerator which is unaided by any external agency. In that of case we consider a perfect refrigerator, perfect refrigerator. What happened here? This refrigerator transfer let q amount of heat from a cold body at a temperature T2 to a hot body at temperature T1. Let that refrigerator transfer what, q amount of heat from a cold body at a temperature T2 to a hot body at a temperature T1. So what will be the, again the decrease of entropy of that of cold body? So what it indicates, we can write here, therefore the decrease of entropy of cold body, is equal to q by T2, and again the increase in entropy of hot body, increase in entropy in hot body is equal to what, that is q by T1. This is the decrease of entropy in cold body, this is the increase of entropy in hot body, and the entropy of that of working substance remains unchanged. Here the entropy of working substance remains unchanged. The hot body entropy, cold body entropy, and entropy of working substance, these three. So total entropy of the system and surroundings, therefore total entropy of system and surroundings is equal to, that is Q by T1 minus Q by T2, since in that point, since T1 is greater than T2, T1 is greater than T2. Here is the T1 is the temperature of hot body, T2 is the temperature of cold body. Always the temperature of hot body is greater than that of the temperature of cold body. So is the total entropy of the system and surrounding will decrease, but which is the against the principle of increase of entropy. We know entropy of that of system is always increasing according to the law, but here the entropy of the system and surroundings decreased, that means it is against that the principle of entropy. So looking at two cases, first one for perfect heat engine, that is the decrease of entropy of that of source and surroundings. Here in case of perfect refrigerator also, that is the decrease of entropy in source and surroundings. This for Kelvin-Planck statement, that for Clausius statements. So in these two statements are very consistent with each other. From first statement it indicates there will be not possible. So I write here, or we can say the principle of increase of entropy is consistent with both Kelvin-Planck and Clausius statements of second law of thermodynamics. Therefore Kelvin-Planck and Clausius statements of thermodynamics both are equivalent with each other. On that basis we equivalent these two statements of second law of thermodynamics. So with the help of this visual lecture we understand what is second law of thermodynamics and two statements, Kelvin-Planck statement of second law of thermodynamics, Clausius statement of second law of thermodynamics, and their equivalence of these two statements by using the principle of entropy concepts. Here how we equivalent these two statements of second law of thermodynamics. So with this useful and informative notes, let me wind up this session. Thank you.